Okay, in each of the following, find the horizontal asymptotes. And so all you have to do here is look at the limit as x goes to infinity. And so that's going to be x squared plus 2x plus 1 over x squared plus 1. And remember, way back when we talked about these limits, we had some shortcuts for limits at infinity of rational functions. We looked at degrees. And here, the degree of the numerator equals the degree of the denominator. And you were allowed just to write n equals d. And when that was the case, we'll be very explicit here and write down the coefficients there. When my degrees were equal, the answer was just the ratio of the lead coefficients. So in this case, 1 over 1, or y equals 1. And so my horizontal asymptote is y equals 1. Same thing down here. So the limit as x goes to infinity of x squared minus 1 over x cubed minus 8. So here we had the degree of the numerator is less than the degree of the denominator. Sufficient to write n is less than d. And whenever that was the case, the limit was 0. And so we have a horizontal asymptote at y equals 0. And then you could take your calculator and check that. Remember, y equals 0 is the x-axis. And so you would be looking, you'd take your calculator out and you'd graph that function. Now comment here, when you graph the function just for checking here, and you press that zoom 6 button, negative 10 to 10. Negative 10 to 10 is hardly extreme left and extreme right. So checking these can be a little misleading, that you might not see the asymptotic behavior on the standard window. So you might be better off graphing on a bigger window so you can see truly extreme left and extreme right. But I just wanted to emphasize here, y equals 0 is the x-axis. So what you would be looking for on the extreme left and the extreme right is that the graph approaching the x and y, or approaching the x-axis on the extreme left and extreme right. But it is worth repeating that zoom 6 window, the standard window on TI-83s and 84s, that's from negative 10 to 10. That's hardly extreme left and extreme right. So just be aware that you might not be seeing the part of the graph that you really need to see. So maybe you set your window to go from negative 100 to 100 counting by tens, or negative 1,000 to 1,000 counting by 100s, so you get a better idea of what extreme left and extreme right might really be. And the last one here, again, we look at the limit as x goes to infinity of 3x to the 5th plus 9x over x squared plus 4. And so here we've got the degree of the numerator is greater than the degree of the denominator. And so that's n greater than d. And when we did this before, we then went and looked at a table to see if this was either going to be infinity or negative infinity. And this is going to be infinity, which, remember, that's a category of does not exist. Other problems might be negative infinity, but what we really care about is the does not exist, that there isn't a numerical answer here. And so I don't get a numerical answer, the limit does not exist. There is no horizontal asymptote. And if you were going to check this graphically, what you're looking for on the left and right is no kind of quote-unquote sideways behavior. On the extreme left or extreme right, the graph is either going up or down, but it's not going horizontal because there's not a horizontal asymptote. Okay, we are now ready to sketch rational functions. So how to sketch rational functions. You're going to do all your increasing, decreasing stuff, just like we did before. You're going to do all your concavity stuff, just like you did before. But now that we're doing rational functions, fractions, that opens up the door for asymptotes. So then 3, find the equations of any vertical asymptotes. And then A, if a function has a vertical asymptote, find a point on either side of the asymptote. That is just a little extra information. You could live without it, but it's a little extra information that's going to tell us what to do when we get to that vertical asymptote. Remember, what made things a vertical asymptote as opposed to a hole was that when we came close to the vertical asymptote, our limits were going to go to infinity or negative infinity, as the case may be, that the graph was going to go up or down. Well, by finding those points, that's telling us whether we should come to that vertical asymptote and whether we should go up or we should go down. 4, find the equation of any horizontal asymptote. Then 5, sketch the curve. A, plot the vertical asymptote along with the points found on either side of the asymptote. B, plot the horizontal asymptote if you found those things. If you didn't, clearly you're not going to plot them. C, plot and label all points found. Label each point with what it is. For example, if the point is a local maximum, write max beside it. Working left to right, starting and ending at any horizontal asymptote, connect the curves with connect the points with the curve using the increasing, decreasing, and concavity charts. Do not cross any vertical asymptote. Horizontal asymptotes may be crossed. And then lastly, check by graphing on your calculator using appropriate window. The graph should reasonably match. And so we are going to do one of these. Sketch this guy. And again, in a test or quiz situation, when the derivatives are a little more complicated, I will give you the derivatives just to save us that step. Now, in your homework, the folks at MyLab Math, they weren't so nice. You got to calculate your derivatives. And if you have to calculate your derivatives, be sure you check them twice. You get that first derivative wrong, everything else is going to be wrong. So let's start this. We're going to start with the increasing, decreasing stuff. Before we do that, yes, we will start with that, but I want to say one thing first. Note, original function is undefined at x equal 1. And if I put 1 into that original function, my denominator is going to be 0, division by 0, horribly, horribly bad. And so what this tells me is there's no point there is no point on the graph when x equals 1. There probably is a vertical asymptote. At x equal 1. Now remember, just because your denominator is 0 or goes to 0 doesn't mean you have a vertical asymptote, which is why I put probably in there. So now let's start our increasing, decreasing stuff. I already have my derivative, so I don't have to calculate it. Critical numbers. Derivative equal to 0. Clear that fraction, equations with fractions. Clear the fraction. So get 5x minus 45 equals 0. Without too much fuss, that's going to give me x equal 9. And then I absolutely cannot find the, forget about the does not exist case. For the does not exist case, we set the denominator of f prime equal to 0. And so I got x minus 1 cubed equals 0. Technically, I could take the cube root of both sides. Without much fuss, we get x equal 1. Now, technically, that is not a critical number. The official definition of critical number says that my critical number must be in the domain of the original function. And as we've already noted, 1 is not in the domain of the original function. But while I'm not supposed to call it a critical number, it's still an incredibly important, vital number, and it has to go in your charts. Any place the original function is undefined, that number is just going to keep creeping up over and over and over again. And it may not give you a point to graph, but it can affect decreasing and increasing and decreasing concavity, so it has to be in your charts. And so let's make my increasing decreasing chart. Let's go on another piece of paper instead of trying to cram it in on there. So increasing decreasing chart. So negative infinity to 1, 1 to 9, 9 to 10. I don't know why I said 9 to 10. 9 to infinity. Test value. And like I said before, some of you, if you've had calculus before, have seen this done with number lines. I've seen some people run their charts vertically. I don't like that, but I've seen it. You know, different people express this, organize this information different ways. I just like this chart method. Pick values here, 0, 2, and 10. And notice here, and I've said this before, in this first line here, I don't have the number 0 because I didn't calculate 0. But for some reason, so many people always include 0 in that first line. Don't use 0 if you didn't calculate it. Now here I'm picking 0 as a test value because that's just easy. And then I plug into the first derivative, which is right here essentially. So if I plug 0 in there, my numerator is going to be negative 45. My denominator is going to be negative 1. That if I plug 0 in there, I'm going to have a negative over a negative, which will give me a positive. If I plug 2 into here, that's going to be 10 minus 45. My numerator is going to be a negative. If I plug 2 into the denominator, my numerator is going to be positive. I've got a negative over a positive, so the whole thing is going to be negative. And then if I plug 10 into there, I'm going to have 50 minus 45 in the numerator. In the denominator, I'm going to have 9 cubed, which is positive. I have a positive over a positive for a positive. If you can't analyze it out like that, you can just plug into the first derivative and see what number you got. But now I can see that f of x is, and because my first derivative is positive, it's increasing. Then my first derivative is negative, so it's decreasing. And my first derivative is positive, so it's increasing. Then based on that, I can decide on my local maxes and mins, which we will do in the next video.